Hi, everyone. Today, I will introduce one of my recent work named multi-dimensional data query for blockchain-based federated learning based federated learning. My name is Yang Jiaxi, and I'm the second year master student at UESDC, and I cooperate with this work with my supervisor, Professor Cao Shun, Professor Xiang Lipeng, Professor Li Xiong, and Professor Zhang Xiaosong. First of all, I want to introduce the motivation of our work. In the incentive mechanism of the federated learning, it is very popular in these days. In the federated learning, there are a lot of work nodes, and we need to motivate high quality work nodes to participate in the federated learning. However, the data owners need to use their own data sets and their own computation costs to update the global model. So no one will willing to participate in the federated learning without any composite. So how to design a proper incentive mechanism for the federated learning is very important. We simply divide the incentive mechanism of the federated learning into three sub-problems: the node selection, the payment allocation, and also the contribution evaluation. And in this work, we focus on the node selection. Like what I mentioned just now, in the federated learning community, there are multi kind of tests that need different data owners to participate in. And in order to protect the data owners, the privacy of the data owner, and the real data is not allowed to liquid to the third parties. So it is really hard for us to select the suitable work nodes in the federated learning. Before I introduce maybe how to select the suitable work nodes, some information about our methodology, I want to introduce the metadata briefly. In the metadata, metadata is the description of the data sets, including like the data size, the data type, and so forth. I want to illustrate one example. The description of the city image set data set may including the disease class, the patient age, and the number of each kind of images. And if we have the metadata, we can select the node according to it. Under coordinators, we also name it that the aggregation services can select the suitable nodes to participate in a specific federated learning test according to the metadata. So, we can, like what I just mentioned, we can use the metadata for the node selection in federated learning. And now what we can do is that when data owners to enjoy the federated learning community, they need to upload their metadata to the blockchain. So the innovation with the blockchain is that it can guarantee the security of a record of the data and generates trust without the need for the third trusted party. Therefore, the metadata on the blockchain cannot be modified by some malicious nodes. And this is the framework of our methodology. The pipeline of our methodology is on my right hand. First of all, the owners need to publish their metadata to the blockchain, and maybe the aggregation services need when it's like to initialize maybe the new federated learning test. It can request data owners from the blockchain and obtain selected candidate nodes. And after that, they can send the global models to the owners, and the owners can maybe using their own data set and the computation resources to update the global model and then send it back to the coordinators. And the coordinators, and finally, the coordinators can update, aggregate them. Yeah. As I just mentioned, you can say that we focus on the step 2 and step 3. This is the process of node selection in the federated learning. However, in the metadata, there's some a lot of challenges. We formulate the selection nodes problem in the federated learning into the maybe the selection, maybe the query problem. However, in the metadata, there are discrete value attribute and also the continuous value attributes. And each query condition may contain multiple dimensional discrete value attribute and the continuous value attributes. Certainly, we can regard the problem as the mixed multi-dimensional query of the continuous value attribute and discrete value attributes. However, existing methods cannot solve this problem efficiently. Yeah. So we modify the structure of the blockchain, and in this blockchain, the structure we name it as the Morker orbit tree, and in this tree extend the advantages of the MR tree and Bloom filter. We use it to the multidimensional query for both continuous value and discrete value attributes, as shown in this figure. And Morker RBG verify the integrity of the whole tree based on the Morker hash tree. Each internal node contains a hash value and Bloom filter and MBR. The minimum bound rectangle is the MBR. The Bloom filter in each node can use to check whether there existing transactions in the current subtrees that satisfy the decreased value query condition. And the minimum bound rectangle covers the range of continuous value attribute of all the transactions of every dimension in this subtree. Yeah. And now I want to introduce the inter-block. We divide the query process into two steps. The first one is the inter-block query, and also the next is the inter-block query. For the inter-block query, we use the recursion method to traverse all the child node of the current node, and if there's no intersections between the special scopes of the multidimensional query condition and the child nodes, then we continue to search down the continuous subtree. Yeah. Just like this. And in maybe the Morker orbit tree, the Bloom filters of each node can determine whether the transactions in the subtree do not satisfy the query condition of the discrete value or attribute. In other words, the nodes and the non-leaf, like this, the non-leaf nodes Bloom filter is the sum of the child nodes Bloom filter. For each discrete value query condition, we started from the root node of the Morker orbit tree, and for all the transactions in the left and right subtrees that do not satisfy the discrete value condition, the Bloom filters in each node are used to find a subtree and not query them. Yeah. And next, I want to introduce the interblock query scheme. We apply the skip list and put forward the efficient inter query method. The architecture is shown just like this. And at each level, the skip list include Bloom filters and maybe the minimum bound rectangle. And for the skip list of the Bloom filters, which is used to query discrete value attribute, and maybe in each level of the Bloom filters in the skip list can use to check whether they satisfy the transactions in the next previous maybe the next blocks. Yeah. And for the inter block query, it is really similar to the idea of for the inter block query. We use the minimum bound rectangle at the head of each block to generate the skip list and propose the efficient scheme for the inter query both for the continuous value attribute and the discrete value attribute. We set a current block at the first one, and donate, and the query process is started from the first level in the skip list and the first block. If the returns is true, we need to check the minimum boundary rectangle of the next blocks. If the false is returned, the second minimum boundary rectangle and the minimum boundary rectangle behind it, and the skip list is queried. Yeah. And next one, I want to introduce the performance of our experience. The query for the discrete value attribute, we verify the efficiency of the query method we propose above, and test the interblock, and both for the interblock and intrablock query performance for the discrete value attribute. The result is shown in the figure A and figure B. Yeah, it is looks like much better. And in figure A, we test our proposed interblock query scheme on the blockchain with different number of transactions from 3,400 and 4,400. And we also put a different number of transactions, the 10, 20, 40 in each block. We choose the scheme without skip list as the baseline method, and we can see that the query time of our scheme is less than the baseline. With each block storing the same amount of data. This is because the fact that the method we propose saves a lot of time for querying unnecessary blocks when using the skip list. In addition, with the increased number of blocks, the efficiency of our plan is more obvious. In the figure B, we put different number in the same set experiment settings, and as for the circumstance which doesn't have the Bloom filter, we cannot quickly exclude substrates that don't need to traverse in the MBR through the discrete value query condition. Thus, we need to traverse on nodes that only satisfy the traverse the node that only satisfy the continuous value query condition and return the correct nodes. And another is for the query for the continuous value attributes, like just showing the C and B, figure C and D. For the query continuous value attribute, it is obvious that interblock query performance of our scheme using RT is much better than the non-exact query scheme. Moreover, the performance result of the continuous value interblock query efficiency for the multi-dimensional data are showing these two pictures. We show that we choose the method without skip list as the baseline methods, and we can see that our scheme perform better than the baseline methods since our proposed methods for interblock query saves a lot of time to search unnecessary blocks in the blockchain by using the skip list. And for the figure A, we contrast the method without skip list for the interblock query processing of scheme, and it can demonstrate that the advantages of the generating and applying skip list for the query process in the blockchain-based Federated. Yeah, that's all. Thank you for listening. If you have any questions, please feel free to contact me through this email. Thank you. Thank you for listening.